Today I'm going to be speaking about the inspection, rating, and rehabilitation of understrength seated hinges on reinforced concrete box girder bridges. Just a quick overview of the presentation here. I'll go through some project background to kind of lay the groundwork for the scope of this project, and then get into the inspection work. And then the final two topics are the unscoped, unplanned for load rating and rehabilitation of the structures. We were brought under contract by the Oklahoma Department of Transportation to do in-depth inspections of 11 conventionally reinforced concrete box girders. This is their entire inventory of this bridge type. They realized somewhere along the line that they had never done in-depth inspections. They'd never gotten inside of them. They'd only done routine inspections, walking the deck and viewing them from the outsides. Obviously thought they'd better take a closer look. Structures were nothing unusual. The structure lengths varied from 180 to 712 feet, scattered throughout the state, with a cluster of them in Tulsa that I'm going to focus most of this presentation on. Maximum span length of 130 feet. Bridges were between 40 and 50 years old, approximately, built in 1978 and up through 1984. Conventional properties, nothing out of the ordinary, 40 and 60 KSI reinforcement, which that is going to be one point I'll come back to later, and fairly low, 3 KSI superstructure concrete. As it turned out, 4 of the 11 bridges required rehabilitation. I'll kind of breeze through this. It's getting late. I know we all want to get home, but the project did run for quite a long time. Again, the initial scope was just for inspection of the bridges, but it turned into a load rating, and then based on the results of the rating, the rehabilitation, and actually construction is just getting underway now. Some of the challenges we faced, won't maybe talk too much about the traffic control. Everybody's probably worked in urban environments. The photo there, the image on the lower left, is of the stacked interchange in Tulsa. A lot of coordination there with the division, and a lot of restrictions on when we were working on the spans over the roadways. The confined space, obviously these boxes were permit required confined space. Entries, the access hatches, it turned out, the ones that were near the abutments in years past, were only bolted shut. They didn't have any sort of locking mechanism on it. A number of years ago, however, they'd realized that vagrants and homeless people had moved into these bridges. You can see their cleaning habits were something to be desired. Maybe kind of looks like some of our dorm rooms from college, or possibly worse, but certainly no trash service. So when we got inside some of these bridges, we had this additional challenge of having to have that all cleaned out. And the final bullet there talks about potential methamphetamine productions that we found. There was evidence of that in some of the bridges. So that really slowed things down, as we had to bring an environmental specialist on board to study and make sure that it was safe. There was no breathing or dermal contact with concrete being a porous material. There was some concern about that as well. It turned out that wasn't a real great issue, and they basically got in there, cleaned all the bridges up, and we were able to finish our inspections on those bridges. A little more about the inspection findings. Really pretty mundane stuff for the most part. The NBI ratings varied from 5 to 7, not unusual for given the age of these structures. We spent a lot of time mapping out the cracks. The great majority of the cracking was hairline. When you've got a bottom slab, web walls, and a top slab all together, your shrinkage cracking is obviously going to be even greater than just in your normal deck or slab bridges. So nothing really out of the ordinary on the inspection findings. Some isolated areas of spalling and delaminations. Just over these next few slides, just a few pictures of what we found. You can see we did a lot of the inspections out of a bucket truck. On the exteriors, nothing out of the ordinary. On the interiors, there were some bridges. Actually, one bridge was still completely filled up with formwork. That was another change order that slowed things down to get all that removed so we could actually perform an in-depth inspection. But for the most part, the insides of the boxes were fairly clean. not much going on. At the hinges themselves, the photo on the lower left there shows the delamination. Again, just a leaking joint, reinforced concrete, not that big of a deal. The deck there, this was the exception and not the rule. The deck was severely deteriorated over one of the hinges. That was something that we needed to consider when we did get into the load rating, because you need to get the reaction of that hinge back up into the top of that slab, and all the reinforcement up there not being bonded with the concrete was a concern. But again, that was not typical. This is the Cincinnati Avenue Bridge, which is one of the bridges in that Tulsa interchange stack that I showed earlier. This was by far the heaviest deterioration we found. But again, no signs of understrength or overstress. This is just a leaking joint. Tulsa does use de-icing chemicals, salts their roads, somewhat milder than other parts of the country, but they go through winters just like the rest of us with the freeze-thaw cycles. The joint above this, the seal was torn, just pretty straightforward stuff. And finally, on the inspection findings, just some of the detailed notes that we took. We documented cracks. We felt like, the first in-depth inspection of these bridges, we'd better have highly detailed notes. So we detailed every crack we found when we were inside of the boxes and outside as well, obviously. But again, all hairline. Didn't really see any patterns of cracking that would be distressing from a overstressing standpoint or the like. During the course of the inspection, the DOT had another consultant team doing all their on-system load ratings. And when they came to these bridges, they got very poor results for the hinge ratings. So since we were all involved in the inspection of them, they decided to ask us for a second opinion, just because the results were so low and so poor. So Oklahoma does their load ratings, God bless them, by the load factor methodology still. They use the conventional trucks, HS20, H20, the federal loads. They also have a family of permit and overload vehicles that we needed to assess as well. For the load rating work, we relied on ConBox, which is now, previously put out by Leap and now owned by Bentley. We found that the controlling moment and shear for the conventional forces away from the hinges were really very high, or not off the charts, but plenty good. 2.4 was the controlling minimum operating rating factor for HS20, and ranged up to 4.5 for the controlling rating factor. So these bridges were really stout away from the hinges. So since we did a quick review of the previous consultant's load rating, we found a few issues that raised the rating somewhat, but obviously we did a completely independent rating of them as well by two different methods. The beam ledge method is described in the LRFD specifications, and it essentially makes reference to the PCA publication, which is the notes on ACI 318. Follow the bouncing ball there. So essentially we were using the ACI specifications to do the beam ledge method on these, which, by the way, didn't exist or was not around when these hinges were designed originally. We also did a strut and tie model of all the hinges. The image in the lower right there shows the dark blue are the tension ties that basically chases the reinforcement in the hinge, and the red dashes are the compression struts. And we went through a couple of different variations and varieties of those, because you can, to some degree, pick and choose where you want to put your struts, not so much the ties, but in the strut and tie method to try to get the best results possible. The results of our rating were fairly similar. We got another slight marginal improvement, but still really lousy results. The strut and tie models ratings came out somewhat or slightly higher than the beam ledge, but again, not good enough news to get the DOT out of this pickle. And one thing I want to show here, really there was a few issues with the detailing of the reinforcement, but as it was shown on the plans. But really, this diagonal bar here is not developed at all. You know, in our strut and tie model, we did what we could to get as much strength out of it as possible, but it doesn't extend all the way up. You're trying to deliver this reaction back up into the top slab, the top the reinforcement in the slab, and it obviously stops well short. So that was one of the main problems. Also, the hanger reinforcement, the vertical hanger reinforcement was deficient as well. Didn't have development issues, but anyhow, those were a few of the problems that we faced. So although we did run numbers, even if the reinforcement was fully developed, it still wasn't adequate. So obviously we started asking ourselves, well, why is this? At least on the analysis side, we did notice, you know, fairly early in the ratings that the hinge details were the same on every single set of plans, although the span lengths varied, the depths of the structures varied over a foot or two. I don't remember exactly, but the reinforcement details, with the exception of the lengths of the bars, they referenced the same detail for every single one of them. And maybe more importantly is some of the span ratios were a little odd because of the roadways underneath, so you had much higher reactions at some hinges than others just because of the layout of the spans. So even though our reactions varied, you know, 200 to 300 kips to up to 400 or 500, the reinforcement details were the same at every hinge. So maybe it was a mistake. So now what? The DOT, you know, we're talking about an interchange here. I'm sorry, I don't remember what the ADT was, but it's pretty high. This is right on the southeast side of Tulsa. And here we go, about to reinforce the bad news that they obviously already had some sense was coming. The DOT did some review of their historical records. They also performed some material testing. They took cores to actually extract the reinforcement. We also went ahead and checked the compressive strength of the concrete, although in reinforced concrete, the strength of the concrete doesn't help so much, at least in this type of scenario. So we did a statistical analysis of the rebar heats from the original construction and the bars that they pulled out. And we were hopeful, I guess I missed a step here, we were hopeful since there was reference to 40 and 60 KSI reinforcement on the plans, and the 60 KSI steel, again, we ran the what ifs, got the DOT mostly out of this pickle. We had our fingers crossed that that's where things were going to turn out. Unfortunately, we got partway there, but not all the way there. But we did some statistical analysis, used the average, you know, subtract off 2 standard deviations, presto changeo, 46.75 KSI. So in the case of the Cincinnati Avenue Bridge, that at least got us away from having to recommend the bridge for closure, and we could keep it open. The image there in the lower right there is actually the posting sign there. The good news, the one silver lining was that bridge carried local city street traffic. At least it wasn't carrying a state route. So the city of Tulsa had that headache as opposed, I guess, to the DOT. But still, not good news. So why is that? We did our inspection work, didn't see any indications of understrength, you know, any large cracks or things that you would expect, you know, all the clues you get from reinforced concrete, they just weren't there. So we did some literature research as we immediately also began the rehabilitation plans with another contract modification. So anyways, we were also asked, you know, maybe as trivia or otherwise, but why aren't we seeing signs of failure? So one report we came across was this Commission of Inquiry of the collapse of the De La Concorde overpass, which I had never heard of. Back in, I believe it was 2006, a bridge in Montreal collapsed abruptly. The structure type's a little bit different than what we're talking about, but it is certainly analogous. The image there in the upper left, You can see this darker gray portion. These are pre-stressed concrete box beams, adjacent box beams. And what they were doing was extending the main span with the drop-in. They had large, reinforced concrete. These slabs were, I believe, 4 or 5 feet deep. And this is actually a 3-span bridge effectively. It looks like a large abutment, but really the abutment is back here buried with massive amounts of concrete acting as dead men to resist the uplift because of the span ratio here. But the key is this hinge detail. When this did collapse, I guess I should say that this was a fatal accident. This bridge, actually, 5 people were killed and numerous people were injured. We all understand the severity of bridge failure, but obviously when there's fatalities involved, it's that much worse. The key detail here is that there's no shear reinforcement in the slab, which by code at the time was okay. So in the hinge zone, or the disturbed zone, it's also known as, there was a lot of reinforcement similarly detailed to what you saw there on the Oklahoma hinges, but there was no shear reinforcement here. So what they found after almost a year of study is that many things, but the most germane to this discussion is that the tensile resistance of the concrete contributed significantly to the strength of the hinge. So I know probably everybody knows that nobody's going to hang their hat on the tensile capacity of concrete on a bridge, but anyhow, one possible reason why we're not seeing distress in the hinges here. But again, when concrete fails in tension, it is abrupt. It's a fracture. Nobody wants to see that. We did have reinforcement, however, but just insufficient reinforcement. Also, the LRFD code already covers it now, but the skew, they found skew increases load effects. A number of our hinges were skewed, and lack of reinforcement and the freeze-thaw cycles were also contributing factors. Another interesting bit was Caltrans just recently went through a similar replacement. It wasn't clear if it was for understrength or possibly seismic, but why they were replacing their hinges. But they had done this. I was just pretty amazed by the fact that they replaced 4 hinges like this in 3 100-hour closures. They picked out 3 holiday weekends and had all the re-steel cages built and went in there and used very high early strength concrete and got it done. It's pretty amazing. You can see the amount of false work that they had staged in there and everything, but did as much prep work as possible. But they were very helpful to us, by the way. We reached out to them. They gave us a lot of good information about this as far as unit costs and construction methodologies and the like. Finally, I'm going to talk a little bit about the rehabilitation plans themselves. This is an overview of the interchange. The hinges in the boxes there, you can kind of see it's not the greatest scale, but I believe it was 9 of the 11 hinges at this interchange were found to be deficient. The DOT decided that if they couldn't run overload vehicles over it, they wanted it fixed. That was the cutoff, and I believe also 1.3 HS20 operating ratings, so somewhat low. This is the plan and elevation of the Cincinnati Avenue Bridge. You can see we took out about a 20-foot swath of the hinges, and we're essentially replacing them in kind. There's nothing fancy here, except obviously we're putting in improved reinforcement details. One thing that we came across was the temporary conditions of the bridge. Obviously, you're going to need the temporary supports under and adjacent to the areas of the removals. But when you release the dead load, when you release the dead load reactions on these hinges, we also needed to check if some of these back spans were going to be overstressed. So we actually had to include on 2 of the hinge removals provisions for temporary supports in the back spans because of potential overstresses and positive bending because of the release of those loads. Just some more reinforcement details. The section views here. We increased the length of the bearing seats to meet current seismic requirements. We also put in a shear key, again, for the same reason, for seismic. These bearings already had Teflon sheets on them, so the bearings were redesigned to current standards, but essentially the same, put back what was already there. Finally, the construction, we put together our estimate, came in at $7.2 million. They only received 3 bids, $8.7 million being the lowest, so even the low bid was 28% over estimate. And I hemmed and hawed about putting this up there because it was a whiff on our part, but if you've ever estimated rehab jobs, I think that you give yourself a little bit of forgiveness on this because they're difficult, and this work is highly unusual. In Oklahoma's inventory, there's very few of these bridges. We relied on a lot of the information that Caltrans provide us, but again, we missed low. But the DOT wasn't too upset with us. They've been getting a lot of higher bids lately. They've been really aggressively replacing their SD bridges out there. They've been one of the worst in the country, and they're tired of that. So they're getting after it. So but anyhow, the contractors just aren't that hungry out there right now. So that could have been as big of a part of it as anything. Construction, unfortunately, they're just really getting underway, so I kind of just have some groundbreaking ceremony type pictures here, but they're staging the temporary support towers out there, starting to do some of the basic excavation and earthwork. Again, the images on the right there, that's Cincinnati Avenue, where they need to excavate out to get down to more competent soils to support the temporary supports. And finally, I'll close with at least one lesson learned on this project, which is maybe more appropriate in the current political environment. Believe none of what you hear and only half of what you see. You know, it's a little disconcerting as a bridge inspector to go out and look at a bridge and, you know, really not find a whole heck of a lot wrong with it. And then you go back and you start running numbers on the ratings and find out something like this, that these bridges potentially should have been closed. For whatever that's worth.